Hi folks, Mr. Long here. I'm going to go over the graph sketching algorithm for polynomial functions using calculus techniques. So what this is a completed graph sketching that I'm just sort of going to go over with you, and hopefully you can see on here that arrow right there, because I'm going to do some, or the pointer, the mouse pointer, I'm going to go over, use the mouse pointer to kind of define what we're doing. So the goal here is to sketch 3x to the fourth minus 32x cubed plus 96x squared. That's the original function. And so what we're going to do, so what would we do with that original function? Well, first thing we do is try and factor it if it's easily factorable. If it's factor theorem or something like that, I wouldn't even bother. Just so don't do that. If you see an easy way to factor it, factor it. If you don't factor it. So for this one here, I noticed that x squared was a common factor, so that was easy to factor out. And so x equals 0, and since there's a square on it, it's multiplicity 2, which means it's a bouncing x-intercept. And this is, of course, on the original graph, right? And then what was left over when I common factored out the x squared was this quadratic, and I checked the discriminant, and it was negative, so there's no solutions for that. So the only x-intercept for this function is at x equals 0. Okay, so that's all the algebra I did. And then over here, what's the meaning of that? Well, there's a double x-intercept at x equals 0. That's what I know. Okay, so pretend that you don't see that sketch there because that's the completed sketch at the end. So the next step, you want to analyze once you get the x-intercepts or the intercepts, you want to sketch the slope function, which is y prime. Okay, sketch out that slope function. So let's take a look at this. So we start with the algebra. Well, y prime is 12x cubed minus 96x squared plus 192x. And that comes from the original function. 4 times 3 is 12. 12. We reduce the exponent by 1, 4 to 3. Okay, good. Then for the next one, minus 32x cubed. 3 times 32, 96. 96x squared. And then finally, 96x squared reduces to 192x, reduce the exponent by 1. So now we factor this and set it equal to 0. 12x was a common factor. Then I was left with the quadratic x squared minus 8x plus 16. Looking for numbers that multiply to 16 and add to negative 8, negative 4, and negative 4. So what we have, the zeros on this, on the slope function, 12x equals 0 or x equals 0, and that's a single. So there's a change in sign in the slope. Remember that this function, the slope function, represents the slope on the original function. So at x equals 0, there's a change in sign. So the slope goes from negative to 0 to positive. And I got that, by the way, off the sketch. So then the second x-intercept is x equals 4, which is a double x-intercept. And what we learned earlier is that a double x-intercept on the slope function means a stationary point. So let's sketch this. So each time we want to sketch it, right? So this is a pretty easy sketch to make. It's cubic, so when the end behavior, it's a positive cubic leading term. So that means it starts low and ends high. We know that there's an x-intercept of 0, which we've got right there. And then there's a double x-intercept at x equals 4, which is right there. Okay, so that was a pretty easy one to sketch. And then we examine this and we look, okay, negative y values on this graph, the slope function means negative slopes on the original. So that means the slope for this part of the graph on the original will be going downhill like this. Then it goes horizontal for a moment because the slope is 0 right there. Then the slope becomes positive. So what does that mean? That means we get a local minimum at x equals 0. And then the slope between, or the y value on this graph between 0 and 4 is positive. Therefore, the slope in the original function is positive. Then it goes horizontal at 4, and then the slope remains positive. And that's why it's a stationary point. There's no change in sign of the slope. Okay, the slope goes positive, 0, positive. Just in terms of interpretation, y prime goes from negative to positive. as x crosses x equals 0? Well, that means x equals 0 is a turning point. That's a minimum. Why? Because we had negative slope on the original to positive slope. Well, it's obviously a minimum. And y prime, that says y double prime. It should say y single prime has a double 0 at x equals 4. Anytime you get a double x-intercept on the slope function, or y prime, you end up with a stationary point. Then we do our second derivative, which is known as the concavity function, and that tells whether the graph is smiling or frowning. So once again, what you need to do is differentiate. What's called differentiate. That's where you take 12x cubed, you go 3 times 12 is 36, reduce the exponent by 1, 36x squared, and so on. So there's your concavity function. What we need to do is to set that concavity function equal to 0 and solve that equation. Now that is an actual factorable one, but the numbers are ridiculous, as you can see, although you can common factor out the 36. Anyway, you end up with, you could just use a black calculator and get the x-intercepts. The x-intercepts of this graph are 4/3 and x equals 4. So you can see very clearly that there's the nice parabola for this, and any x-intercept on a concavity graph is a point of inflection. If the slope function and the concavity function share an x-intercept, that means it's a stationary point. Okay, so these are your points of inflection. If the y value is positive on the concavity graph, the original function is smiling or concave up. If the y value is negative on the second derivative, which we call the concavity function, the original graph is frowning. Okay, so this graph smiles, frowns, smiles. Now we have enough information to go back up and draw our original graph. We knew that we had a minimum at 0, we had a point of inflection at 4/3, and we had a stationary point at 4. So this is reasonably easy to sketch. I know the end behavior is high and high because its leading term is 3x to the 4th. So that means 3x 4th comes down, it bounces at 0, which is a minimum, a local minimum. And then there's a point of inflection where it changes from a smile to a frown at 4/3, x equals 4/3. And then once it reaches 4, the concavity changes again. Okay, folks, so what you want to do maybe is to go over this video and just sort of work through this question even, and then you're going to be assigned about another 3 questions from the textbook, and I want you to do the exact same process. Okay, get the equation for the slope function, set it equal to 0. Get the equation for the concavity function, set it equal to 0, and solve. Okay, in each of those cases. And you always want to draw the slope function and draw the concavity function. Okay, good luck, folks.